Hello everyone, we are Team 4, consisting of Carl Cantingwalla, Philip Downey, Lauren Newton, and myself, Daniel Zhu. This presentation discusses the motivation, setup, and results of a study involving set-based two-dimensional model predictive control of a rocket landing on a moving target. For this investigation, model predictive control techniques were utilized to land a simplified rocket model that is unconstrained in both the vertical and horizontal axes onto a moving landing area, which is modeled after the drone ships that SpaceX utilized to perform rocket landings over water. The goal of this is to improve the economic efficiency of space travel as well as to reduce the cost of deploying structures into space. This involves developing formulations for affine-based reachability analysis. To do this, the system dynamics needed to be linearized to enable the implementation of quadratic programming for optimal control. The main goal was to analyze the feasible target conditions for a successful landing by performing a gridded simulation on the amplitude and frequency of a series of sinusoidal trajectories assigned to the moving landing area. Lauren will now go into more details about the dynamics of our model.
The full nonlinear model of the rocket's dynamics in two dimensions invokes the global pitch angle theta, horizontal x-coordinate, and vertical z-coordinate, as well as the derivatives of these parameters in the state. The inputs are the rocket thrust and the associated gimbal angle, delta. Considering a one-dimensional problem, ignoring x dynamics, these dynamics may be linearized using small angle approximations and using a change of variables to remove a quadratic input term. However, in two dimensions, a residual quadratic input exists that resists linearization. Instead, the reduced model here is adopted considering only x and z coordinates and velocities in the state. The quadratic change of variables is used to make the system affine, and the global angle is restated as an input for the purpose of analysis. The equation at the bottom is then used to extract the physical control input, the gimbal angle delta, from this variable. Moreover, limits on the gimbal angle are applied as a second-order rate constraint on the global angle by this dynamic equation. Controllable sets may be defined for the affine dynamics and constraints. The one-step function listed here may be called repeatedly to determine the n-step controllable set. An interesting note of the affine dynamics is that they are not control invariant. The constant gravity term pulls the controllable set away from the target at each time step, as seen in these plots for the isolated z dynamics. In order to drive the rocket to the target rapidly in n steps or fewer, the union of the n and lower step controllable sets is used as the terminal constraint in the optimal control problem. For control invariant dynamics, this is simply the n-step controllable set. However, for non-control invariant dynamics, this union operation is not well defined for these polyhedral sets as it is not a convex operation. Instead, the optimization problem is iteratively solved for each controllable set individually as the terminal set, beginning with the one-step controllable set and increasing the number until a feasible problem is solved, returning an optimal input. Carl will now discuss the switching strategy of our MPC scheme.
This investigation utilizes a three-step control switching strategy to alleviate some of the issues brought forth by the dynamics of this system. It also serves to create a more robust control system that can handle a larger array of anomalies. Our first stage of control is to attempt to land the rocket using a standard MPC approach, where, at each discrete time step, a constrained finite time optimal control problem is solved between the current state and the target state. Solving the CFTOC problem at each time step allows the target state to be changed as the barge moves. If there is no feasible solution, the terminal constraint is then replaced with the reachable set defined by the number of steps remaining in the simulation window via the iterative procedure that Lauren described. If once again there is no feasible solution, we will remove the terminal constraint entirely, and our input sequence will be driven by the objective function alone. Throughout all stages of the controller's design, the objective function remains the same, and only the terminal constraints are modified. Philip will now discuss the results of the simulation.
The rocket controller was validated by simulating over a variety of barge position and velocity combinations by assuming a sinusoidal motion characterized by amplitude and frequency. A moving target causes the controllable sets to become time variant, complicating the controllability relationship and motivating this brute force gridded approach. Here, feasible landings are shown as green O's and infeasible landings are shown as red X's. In this script, the feasibility of a landing is determined in the last 5 steps of trajectory, as the rocket will either satisfy or err of the terminal constraints. The contour lines on the plot indicate the maximum velocity for a given amplitude and frequency pair, and the minimum velocity is known to be 0. In the lower left quadrant of the plot shown on screen is the range of estimated physically likely conditions that the barge may endure in the ocean, namely an amplitude of between 0 and 2 meters of horizontal motion at a frequency ranging from 0 to 0.08 Hz. The controller is able to land the rocket over a densely gridded simulation and so can be assumed to land throughout the region. Extending beyond the realm of the physically likely are a series of tests to validate the efficacy of the controller. Here, a number of trends become apparent. Namely, when the barge moves faster than approximately 2 meters per second, the rocket fails to find a feasible landing pattern. Additionally, trends of feasibility failure begin to appear at higher frequencies, independent of the amplitude. Lastly, there is a grouping of infeasibility about 0.13 Hz. Upon analyzing plots of each state of the rocket and barge throughout the simulation, the failure to land can be attributed to the barge changing direction as the rocket begins its final descent, suggesting that in future tests, perhaps the barge phase should also be gridded over. To this end, further research will also include an estimation of the barge state within the rocket controller, which would enable smarter landing sequences optimized for position and velocity.
This animation shows the performance of our control system for landing a rocket starting at a height of 1,200 meters. It also starts 200 meters laterally offset from the target area. The target area is moving with an amplitude of 8 meters at 0.08 cycles per second.
In sum, the context of this report encompasses first the presentation of a linearized model of a rocket, along with the assumptions made to enable optimization using quadprog. Second, the development of an affine-based reachability set function is demonstrated to accompany a CFTOC iterative MPC controller. Lastly, the controller is validated through simulation of landing the rocket on a sinusoidally oscillating barge. Results indicate that the physically likely conditions are feasible for this controller.